So I'll explain you my lecture plan. Now, Michelangelo nicely introduced the theory from a general point of view, its origin from N=4, its main feature, and he presented the computation of some scaling dimension non-perturbatively in this theory. What I want to do is basically give you another perspective on this class of theories, and I will concentrate on the Bicolor theory, so the simplest that he introduced. And I want to give you another perspective in a sense that I have two messages I want to convey. The first is a motivation. And this motivation related in general to the computation of Feynman integrals, but I want to say something a little bit more ambitious, is the So, okay, so I can go on? I can also, okay, okay, nice. Tampone rapido. Prova. Ci siamo? Okay, so as I was saying, I want to give you another perspective on this theory, point of view of motivations. I want to provide you some good motivation, why to study these theories, which are so exotic, are non-unitary, are very strange animals. Okay, sure, they have this integrability property, but who cares about studying these theories, really? I mean, they are very simple and they can be solvable, but really, what do we do with these theories? So, some motivation. Related to higher point correlators. In n equals to 4 super young mills. So n equals to 4 super young mills have been introduced at least by Michelangelo today, and I will assume more or less, for sure, many people in the audience know this very well, but I will, for the rest I will rely on Michelangelo's introduction. And the second point, the second message, is that you can use spin chain methods to compute high loop Feynman integrals. Okay, so okay. This is all I want to say. Okay. So let me start. To go concrete. Now, in the fishnet theory, the biscalar theory, which is described by two scalar fields, let me call them X and Z. Okay, these are complex, and how Michelangelo was showing, they have only one vertex of interaction. Okay, so you have like X bar, Z bar, X and Z, with a coupling in front. Okay, so he called it psi square. So these are matrices. They transform in the adjoint of SUN. So they have n times n elements. They are big objects, and actually we consider n going to infinity because we want to study only planar graph. So the message is that in the planar limit, due to this vertex and the absence of its complex conjugate, the bulk of a large Feynman integral has a fixed topology, which is that of a square lattice. Okay. So in practice, any Feynman integral, okay, at a certain order, in this case we have what? 12 powers of the coupling, is this. This is the only Feynman integral you can have, plus boundary conditions. Okay? And this boundary condition is decided by what are the operators which enter the correlator. In particular, so this restricts a lot, of course, the integrals you can have, and in some cases, this reduces the number of integrals that enter the perturbative expansion of a correlator to 1. So let me draw you 2 examples. Generally speaking, we consider in this large and limit operators which are traces of products of fields. Okay, so let me consider this operator, for example. For example, trace of x to the L, which somebody will recognize to be protected operator in 1/2 VPS protected operator in n equal to 4 super Young-Mills, but here, as Michelangelo explained, it is not the case. Michelangelo was exactly studying the 2-point function of this type, okay? Okay, which are described by this type of diagrams with the wrappings or wheels, how we called it. Okay, so it's not protected. And I want to build a 4-point function. Let's consider the simplest higher point correlator 4-point function using this kind of operator. So I can have trace of x to the L, trace of z to the k, for example, trace of x bar to the L, trace of z bar to the k. Okay, it's a legitimate correlator. So how do I draw this kind of correlator? Well, the theory is planar, so all the Feynman integral that I can draw will lie on a sphere with 4 punctures, because I have 4 operators. So these 4 operators are located in 4 positions. Therefore, I can write my sphere with 4 punctures. And what do I know? I know that in the bulk of this, so there will be Feynman diagrams lying on the sphere, because they are planar. And this is the Feynman diagram that I will have. It's the only thing I can have. Okay? And so it must be connected to this external field in these points. Okay? This is point 1, point 2, point 3, point 4, which are the insertion. 1, 2, 3, and 4. Okay? So what can happen here? The only thing that can happen is that I have the fields x propagating in one direction, the field z propagating in the other direction. And they cross in this way. For example, here I have L equal to 3 and K equal to 3. Well, if I have K equal to 4, well, I would have this, right? But I can actually have more. This is not the only Feynman integral that I can have for this kind of function. Because, of course, one of these line of these propagators could pass in the back. You know, this is a sphere. So I can a sphere, one puncture here, then I have one other in the back, one here and one other in the back. So I can have one guy passing downstairs and coming back here. Right? And okay. So, but due to the chirality of the theory, of the interaction, only from one bundle this can happen. Because if it happens from the other bundle of propagators, I would reproduce another square lattice behind, but this vertex here would be the wrong one. Because if here it's this, in the back will be this. But this is not present in the theory, because it would be z bar, x bar, z, x. Okay. Moreover, I can have other corrections, which are the 2-point function corrections around the puncture. Okay? So the wrapping that happens here, they can happen around each puncture, because I have these operators. And this is, I can simplify my life. For example, adding, for example, a field x bar here and a field x here, which make this operator protected. Why? Because, again, it's always the same reasoning. Okay? I add another propagator which goes the opposite way, and therefore my wrapping cannot close, because it would need here the wrong vertex if we are in the planar limit. Nice. So same story. Could go with zeta. in order to protect this around the correction around the punctures with wrapping. So the message is that I can build correlators of single trace operators, which are therefore correlators which are well defined in principle in an n equals to 4 theory, because trace of power of field is gauge invariant operator, which are described by a very simple class of integrals, which in this case is given by the so-called Bosodics integrals. Okay, Bosodics integral is this Feynman integral, where every time I have a segment, okay, this is 1 over x squared of the distance between the extremes, and every time two lines cross is an integration point. Okay. So you see, the only thing that can happen inside here is this kind of graph. Okay. Times eventually, once again, there is a propagator passing in the back, is just a propagator. You just have to multiply by it. It doesn't cross anything, it's not integrated. First thing. Second thing, I told you the topology is always the same. So what, for example, if I consider, so to say, excitations, so to say, of this type in one operator, okay? If I consider one operator of this type, and of course the complex conjugate, and so on, what will be, what would change? Not much, okay? Because the topology is still the same in the bulk. So I should analyze only what changes around the puncture. So once again, for example, I have my X fields, and here, yes, let's consider my X fields. And for example, here I have my field Z, so I have 3 field X, okay, and my field Z. And this field Z can only in one specific direction, because of this unicity of the vertex, spiral in this way. And for example, being absorbed in another point, or going on, okay, and yes, for example, here I can have one field Z emitted from here, starting spiraling and coming back. Okay, so this would be x3z, and this would be x3 bar z bar. Okay, but finally, if you look from far away, it's again a square lattice. So you see, it's simple. It's simple, quite simple situation. So it is very important to be able to compute Feynman integrals which are portion of square lattice with certain boundary condition. If I can do this, I can compute, in principle, all the endpoint correlators in this theory. This is the message. And the first place to start with is this guy, Bosodics integral. But, sorry. But this guy now has another story, which is a strong motivation. Well, first of all, I can simplify even more my life, since I'm in the fishnet theory, which is not a gauge invariant theory. As explained, the gauge field decouples, so the SUN symmetry of the theory is purely global. So I have these fields which transform in the adjoint, but there is no plus I delta mu u dagger u. Because it would not be a symmetry, I miss the gauge field, which fix everything, right? So with this, which is only global, I can also consider correlators of a single trace with splitted points. So the counterpart of the Bosodics integral would be this guy, where x is in point 1, z is in point 2. Then 3 and 4, okay? So you see that in this case, really the only Feynman integral entering the correlator is this. If L is equal to 4 and K is equal to 3, for example, okay? So I don't even have to worry about any wrapping and any nothing, okay? So this class of Feynman integrals, then I can generalize. For example, I can do even more point splitting. I can consider any permutation of the fields inside here. and build a graph which in the end will be just something like that. Okay? It's gonna be a square lattice with some boundary conditions. Okay? I can split the points, permute, and so on, and I will always obtain this structure. Okay. But now I want to say what I want to say is that the only two results I want to present are: one, how to compute this object. Now I will motivate why it is interesting beyond this exotic theory. And secondly, I want to say that for these diagrams, even for the most special one, I can extract the leading log in the OPE in a very simple and playing a little combinatoric game. Okay, if I have time. So let's start let's now say this. Why these integrals are important in n equals to 4. And their importance is related to the fact that in n equals to 4, it is actually possible to compute a class, but let's say not much more than one. It's a very restricted class of 4-point functions, non-perturbatively. Simplest. It is actually possible to do a little bit more than this, but what I'm gonna show you is a very, very important representative of a small class. And I don't know if somebody in the audience knows other theories in higher dimension, like 4-dimension, unitary theories where 4-point functions have been computed non-perturbatively. I don't know, other than this. And this is a result, by the way, is important to mention here, by first of all by Frank Coronado. Okay. And what's the point? Let's consider 1/2 BPS operators, which are operators whose scaling dimension is protected. Okay, so gamma g squared is equal to 0. They don't receive correction to 2-point function due to supersymmetry. And I can write them in this way. What do I mean by this? N equals to 4 as a SU4 R symmetry. Let me say a SO6 R symmetry. Okay? I can spell it in this way. In the sense that, concretely, I have 6 scalar fields, okay, with an index. Okay? Yes. And some of the scalar fields, and these 6 scalar fields can be combined into 3 complex scalar fields. 2 of them are the ones which actually appear in the fishnet and they survive after the deformation. And if you pair this vector of scalar fields of 6-dimensional, 6-component vector with a vector y, which is null of 6 components, well, then therefore this for sure it is a protected operator of 1/2 BPS type because it is a symmetric and traceless combination of fields phi in respect to the index A. Okay? This is just the recipe. This y is called polarization vector. Now, if you choose accurately this polarization vector in the 4-point of your correlator, so here I have like trace 1 polarization vector time field to a certain power k in the point x1, and so on for x1, x2, x3, and 4. Okay, with y1, y2, y3, y4. An accurate choice of this polarization vector, for example, gives me the 3-level diagram with all fields connected along a square frame. Okay. So here I will have a k over 2 propagators. K over 2 propagators, k will be even, of course, otherwise. K over 2 propagators. Okay. So if I fix things in this way, and I consider k which goes to infinity, k which is very, very, so-called very heavy BPS operator, Now there is a very important observation, which was kind of experiment, I mean, was a perturbative observation, and coming also from very, very sophisticated methods of integrability, which I'm not going to discuss in any way. And these observations are very much related to the Bosodickson integral. Or actually, the Bosodickson integral helped a lot into this point. And these observations are the following. Well, first of all, the perturbative expansion of this diagram, of this correlator, contains only ladder diagrams, which are a simple case of Bosodickson integral. If you consider Bosodickson integral of this type, so where you have only one propagator, one direction, these are ladder Feynman integrals. You don't see the ladder, of course, because you should go to momentum space and it will look like a ladder. Okay? And this is absolutely strong statement, because you would have already at 3 loops, you would, by normal constraints of the theory, you would have many more diagrams. Okay, more complicated diagrams, please.
So maybe you will get to this, but when you said earlier that you are going to show us something non-perturbative, so you are still at large N, and also now it seems large K?
Large K, that's true.
I mean, like, it's non-perturbative in one coupling, but you are in a very specific large N limit and kinematic regime, right?
That's true,
okay.
yes. Absolutely. It's this class of results where we can compute things non-perturbatively in the toothed coupling happens into 2 situations, as far as I know. First, when I consider, either if I consider very heavy operators, or if I consider special kinematics, namely some light-like distances into this polygon of propagators. So, from what people know about n equals to 4, the diagrams which can enter the perturbative expansion, they should have some special property called dual conformal symmetry, but anyways, they are way more than ladders and products of ladders. Here the observation is that there are only ladders in this limit.
So I missed it. Why did you choose K over 2 and K over 2 size? Can I not say, I don't know, I move some propagators on the sides and I move from the top?
I want this configuration. I choose the polarization vectors. Okay. Of course, you know, the propagator between 2 fields has a certain index structure respect to these SO6 indices, and I choose them such I have a very heavy bundle in the limit k going to infinity, because these effects happen with this configuration.
But I guess maybe another way to phrase the question is, could you have had k plus m over 2 in the horizontal line, k minus m over 2 in the horizontal line?
As soon as I miss
finite and say send k to infinity.
Yes, definitely.
Okay.
Definitely. It's not as small. If k is very big but finite, then this difference will show up. But at a number of loop which is of the order k, say. Otherwise not. So first thing, only ladder diagrams. Second thing is the fact that with this special configuration, it's not hard to convince yourself that when you put these 2 points very close to each other, or these 2 points very close to each other, so you consider it's called U-channel OPE, you have some constraint from, you have some analytical information, because you imagine that, you see, there are no propagators stretching here. So you imagine that this OP channel is dominated by double trace operators. And if it is dominated by double trace operators, it gives you some analytical constraint known as Steinman Relation, which I can phrase in the following way, that when you take the OPE, the maximal log in the, so when you take your OP, you are taking a cross ratio of this 4-point function to go to 0 or infinity, okay? And the maximal power of log is log of 1. This is a truncation, it's very strong information. Usually one has infinite powers of log if you go on with the coupling, okay? With the powers of the coupling. So you really have log of V multiplying a power of the coupling, a function of the coupling on the power, plus F1, F2, without log. And this effect can be explained in terms of planarity, of double traces. It's an effect that always happens. It can be explained in the question section. I would rather give the information. Now, in order to compute this function, there is a third point you need. What I want to say is, if you consider these 2 points, this is enough already to build an ansatz. So you can write an ansatz, a linear combination of functions that you know, and then you would need some data to fix them. And data would come from the light cone behavior of this correlator. But this light behavior can be studied pretty simply, also with new methods recently introduced, but also without, in this simple situation. The point is how to build this ansatz, and here it comes Bosodics diagram, because Bosodics diagram is indeed the point is. Bosodics diagram, these are Bosodics diagrams, okay? Others are Bosodics diagram, but not only. Bosodics diagram is indeed an object which should enter this kind of, the perturbative expansion by its symmetry, should enter this correlator in the perturbative expansion and satisfies 1 and 2, okay? Why? Because the Bosodics diagram of size m and n is the determinant of a m times n matrix of the ladder integrals okay, I plus j minus 1 plus n minus m, I would say. Okay. This is the generic element of the matrix. L is ladder. So L of A is Bosodics diagram 1A. This is a very strong result. Can you imagine that this diagram here is a determinant made of this kind of diagram here? It's not trivial at all. And there is integrability underlying this computation. What I want to say is that if you can study from purely fishnet Fourier transform simple methods this object and obtain this result, then you know that this kind of objects should enter the perturbative expansion here. Or at least it makes sense that it does. It has the right symmetry to be there. And it is made of only ladder diagrams, and it actually satisfies Steinman relations. And this gives you a strong idea that this is the right basis of integrals that should, of functions that should enter the ansatz. And indeed, the ansatz for this object is the following. GUV can actually be written, and this is related to this k going to infinity, but it can be explained in the question session. It's actually the square of a function. And this function, for this function, we have this ansatz. We have this ansatz, which is you can sum in m, g squared to the m, okay, and then you can sum in, then you have other indices. Okay, you can sum in n, which goes from, say, square root of m, okay, yeah. So m will go only on squares. Yes, to infinity. Yes. Sorry, from 0 to square root of m. And I will have another index, which is, say, Okay. Let me make things simple. Okay. C M N. Okay. So let me phrase it in this way. So in the perturbative expansion, you have expansion in the coupling, and for each power of the coupling, you have a sum, which is a sum of indeterminate of ladders. And this determinant of the generic element in this determinant of ladder is I plus j minus 1 plus m minus n. That is the Bosodics diagram, or other integral, other determinant where there is a change here in the shift. You can also introduce a integer shift in the column. But Bosodics integral gives you the intuition of the type of functions that are made of ladders and satisfy the Steinman relation. Now, there would be an integrability interpretation of this type of formula, which I'm writing very roughly. But the important thing is that I have a double sum, namely, which here I wrote reverse, because it's maybe better in this format, but one could write n from 0 to infinity, and for every n, you have a perturbative expansion. Let me do this, because I think it's clear. The perturbative expansion starts from n squared and goes to infinity. The first term in this perturbative expansion, g to m, multiplies the Bosodics of size m n, and then I have other terms. Okay, so yes, and then I have yes. Let's do like this. Yes, the first term is g squared to the n squared. Okay, and then I have other terms of higher coupling, so 2n squared plus something, which are determinant of ladders where I have also some shift, non-zero. But these are this kind of object. So it is actually a very strong information to know this type of diagram. Okay. Now, you have this expression, and using only light cone behavior, if you take the light cone limit of this expression, z and z bar are, of course, inside here, the ladders, you don't kill enough information, say that CMN survive. Okay, so with light cone data, you can fix these conditions.
You know, just a small thing. So we are at large N, right?
Sorry?
We are at large N now, right? So I just want to say the coupling there is the 't Hooft coupling or a Young-Mills?
't Hooft coupling.
Ah, okay.
Okay, so with light cone information, you can completely, so fix completely this O and obtain your non-perturbative expansion in the sense explained to Alessandro of this object. This is a remarkable result. So now,
maybe about, again, the word non-perturbative. So this is actually, as it's written, it's a perturbative expansion. It's an expansion which may or may not be convergent. So is it, is anything known about like the really non-perturbative or whatever resurgent properties of this series, or?
yes. Yes. So these objects are studied also as strong coupling, and this is done with supergravity using the SFT correspondence. They are studied with 10-dimensional supergravity. So I think this object is related to the minimal surface enclosed in a folded string.
But I guess my question is a bit different. So if I want to get this observable for, let's say, g equals 0.93, okay, whatever, or g equals square root of 2, something like that, right? Can I do that? Is there a way to treat this thing either by resumming the series or by some other technique to treat this parameter as something parametrical that doesn't need to be, you know, summed over?
Yes, yes, yes. Yeah, Alessandro, yes.
Bessel functions.
Yes, yes. No.
I think they do it, like they write there's some Fermi gas and then they argue that this should be the
yeah, but
form.
right. But then you have to solve this.
Yeah, no, of course.
So the expression,
he was asking if there is any way to write this. There is, but you don't know how to do it. Like you don't get a number, you get a representation.
What I wanted to say is that you get really the number if you are special kinematics. Okay? If you are in the null square limit, that is, for example, these null edges. These 4 edges lie on the light cone. Well, this behaves basically like a Wilson loop with 4 cusps. So really this object that I'm writing, O, now of course null limit means that I'm doing something with this cross ratio, for example, z going to 0, z bar going to infinity, and some tuning of the coupling, and this object is, I should say what is S, but it is a very simple object of this type where S square is G square log Z bar, log 1 over Z log Z bar, okay? It's very simple in this case. Then what can you do if you take only 2 edges which are null, we come to what Alessandro was saying, that instead of getting this object, you get something a little bit more complicated, which, as far as I know, at least in the most general, in the general situation, so-called octagon with ridges, to refer to what you say, is not computed. Like there is this story of Fredholm kernels, and only when you are really in the full null square you can compute. Otherwise, it's like switching on the temperature in this Fermi-Dirac distribution you are mentioning, and it's not done. But okay. Now we want to do the exercise of the fishnet, because I argued all the time that fishnet is useful for something which apparently is completely unrelated. So we come to the second point. And last. No, next to last. Okay. So Michelangelo already introduced a bit this idea of mapping a computational Feynman integral to a spin chain, or to a graph building operator, how we called it. So, first of all, let me draw the diagram. Okay. So this is maybe is a bit unhappy choice. Okay. This is a bit less symmetric. So here is point 1, point 2, point 3, and point 4. Okay, I can reduce this problem making a conformal inversion, for example, conformal transformation. For example, I can send point 2 to 0 with the translation. Okay, of course, every time I make a transformation, I should say 1 prime, 3 prime, 4 prime, but please have mercy on this. And now I can make an inversion, for example, which is this transformation, and sending this point to infinity. And what I will obtain is this diagram. Sorry, 2 lines, and 1, 2, and 3, plus a bunch of propagators which are not integrated, times a bunch of propagators which are not integrated. But this is the object I want to compute. Okay, 1, 3, and 4, but I put 4 to 0, okay, with another translation. So finally, what is the point here? If I'm able, you see, this is as a iterative structure. Okay. So if let me consider this operator. If I iterate 4 times this operator, I obtain this diagram. Okay, this is point 0. This is an integral kernel which acts on a function here of 2 coordinates and gives a function of 2 other coordinates. Okay. These points are y1 and y2, and this function is f y1, y2. Okay. Let me iterate 4 times, I obtain this object. If of course, then I put these 2 points to be equal, and the 2 last points to be equal to 3, but this comes after. So if I can diagonalize, express this integral kernel, expand it over a convenient basis of function, I can compute this integral, basically. If I can diagonalize it. If I can diagonalize, it's clear that being an iterative application, every application will just give a power of the eigenvalue of this basis of eigenfunction insert. Okay. Therefore, this object to the L, which means applied to itself L times, if I insert the basis of eigenfunction, which depends on some continuous and some discrete labels, okay, I sum over this. Acting on the eigenfunction will give me eigenvalue, so will become immediately E UL to some power L times F and F. Okay. Okay. So I will transform this complicated structure in an expression, and of course here I have a completeness sum, so I will have to deal with the fact that I have to take this sum. But long story short, in the case when in the situation of the ladder, so when I have only operator with one horizontal line, this is problem which is very well known, because I have what is this object is like 0, x, and this is the integration point. Now this is clearly as an integral operator, this is y minus x to the square, and here I have x squared. Okay, this is a rotation invariant acting on one variable. I can decompose it over spherical harmonics. Okay, so actually I can actually rewrite this object modulo apart from a constant. If you look at how it acts under Fourier transformation, it's pretty clear that this is 1 over x squared nabla to minus 1, just to make things simple. So it's clear also that the solution will depend only, I mean, you can work this out, will depend on continuous parameter, which regulates the scaling behavior. Okay. The scaling behavior of the function, R is modulus of x, times, in principle, you have your spherical harmonic, but you don't really need a spherical harmonic because the problem is a rotation invariant, so you need only the zonal spherical harmonics. You know, when you take spherical harmonics and you sum over all the quantum numbers of type M. Okay. Or if you prefer, it is a irreducible symmetric tensor, whatever. Okay. This technique is very well known as a Gegenbauer polynomial technique, basically. So it's very simple function. That's the message. And this object can be written as x mu 1, x mu L, symmetrized over these indices. And these are normalized vectors. Symmetrized. Yes. Symmetrized. Okay, so this is well known. I mean, it's like expansion of the Newton potential with zonal spherical harmonics or Gegenbauer polynomials, how you prefer. Now, and there is no integrability here. I mean, it's one side. I mean, one particle which moves in whatever potential. I mean, you don't need much. But when I have more, 1, 2, 3, 4, and now it's a problem. So how can I expand a system? Instead of an atom which I expand a hydrogen atom in spherical harmonics, now I have several of these poles, and I should find a basis of eigenfunction. But fortunately, this operator is actually a transfer matrix, as Michelangelo was mentioning, of an integrable spin chain. Now, what Michelangelo was considering was the situation in where there were closed boundary conditions, so I had a circle of this type. Here I have open, but it's possible to show that it's just a strongly twisted version of the spin chain where the twist is integrable. Namely, I maintain integrability properties. And even more, because this is just chatting, you know, I can really solve this problem. This Michelangelo didn't show you the solution of this when there were more than 2 legs, because nobody can do this despite integrability so far, as far as I know. But this I can solve. And the solution is the following. I'm not going to write, of course, the explicit solution, but I'm writing the equation, the remarkable equation which underlies this solution. That if I call this operator gamma of n, because I have n of these legs, okay, so I will have a Bosodics with n horizontal lines, I can find a transformation of this type. I can find an operator lambda, which acts on lambda of size n, so-called of size n. Let me write it like this, so E, which depends on some values. Okay, this is the equation. My operator with size n acts on another operator of size n, but this operator acts on n minus 1 variable. Okay, so maps operators from n variables to n minus 1 variables. Okay, here we have n variables, n points. So this is acted on in n points, and here it acts on n minus 1 points. So you lose one coordinate, but you gain some parameter. And what happens? It produces a number. This is just a number, times himself, acting now on the operator you want to diagonalize of size n minus 1. And this allows you to solve iteratively the problem, because if you iterate this, you end up in the case when n equals to 2, then you have n equals to 1. So you have just to find this operator, but it's possible, the message is possible to find this operator. And this equation, I would dare to say that this is a separation of variable equation, and then I will never, apart from the question session eventually, explain why. But the point is, I can really then write the eigenfunction like lambda n minus 1, lambda 2, and finally my function here, ful, where this guy, lambda n, will depend on un ln, this will depend on un minus 1, ln minus 1, and so on, and the first guy will depend on u1, l1, and the spectrum of the operator is factorized respect to these values, because when gamma passes through the first layer, produces E in un ln, carried by this, and then times E un minus 1 l minus 1, right? So we are ready to write the expression of the Bosodics integral, because Bosodics integral, okay, in this case I have 3, m is equal to 3. These points are at infinity, so I could also cancel. Okay. This is equal to eigenvalue u1 l1, u2 l2, and u3 l3. Okay. How many times? I have 1 time the operator, second time, third time, fourth time. So to the power 4. Okay. And then I have, of course, since I'm decomposing an operator over its basis of eigenfunction, I have the completeness sum, right? So I will have the bra, my function, psi of the u, and the l's, which is this gamma n minus 1, lambda, what is this gamma? N minus 1, and f, okay, of u and l, psi ul. Okay, and then I will have the summation, which is a summation over L and U. Okay, L discrete index, U continuous one. So I have integrated the real axis in U and just summation from 0 to infinity in L. And then of course I have the measure, but the measure how I compute taking the scalar product of these two functions. This is a complicated problem. Worked out, I mean, it's not really complicated. You should work to get it. And this measure is, and here you can recognize something, product from for I, which goes from 1 to m is equal to 3 in this case, okay, of Li plus 1. This is you recognize the dimension of the eigenspace of spherical harmonics in 4 dimension. Okay, so this is just a multiplicity due to the radial, due to the angular invariance of this operator. The fact that this operator depends only on distances and there is nothing angular. Okay. And then there is a product J different from I, again from 1 to 3, so to M, of Ui minus Uj square plus Li minus Lj square over 4, and Ui minus Uj square plus Li plus Lj plus 2 square over 4. Okay. And this measure is inside here, mu UL. Okay. Okay, now I can write the last passage. Okay, let me specify what is EUL. Very simple object. Okay. And finally, I have to say one last thing, that I am writing here the functions, but the functions are functions of 3 points, right? Because the operators act on 3 points. Then when I compute the Bosodics integral, first of all, I delete this guy, this vertical propagator, which was not integrated, so I just have to multiply for it from outside, and pinch together these 3 points, and pinch together these 3 points. Then if I want, I can also make back the inversion to restore these 3 points, which were sent to infinity. But, okay, so this is just, it cannot be seen if we use only conformal cross ratios. The point is that this eigenfunction, and believe me, it's remarkable because if you repeat this computation in higher dimensions, and you can, this is not the case. So in 4 dimensions, it's remarkable that when you have a function of x1, xn, of u and l, and you reduce all this point to the same point, this becomes the product of the single-side function. So f in u1, l1, x1, f un, ln, xn, okay? And, sorry, x1. So you end up with this bunch of function, which therefore under completeness, this object here becomes basically x1 square over x1 and 3, right? So over x3 square, I, u1 plus u2 plus un, so completely factorized, and Gegenbauer polynomial of index L1 in cosine of theta, Gegenbauer polynomial of index Ln in cosine of theta, okay, where cosine of theta is z over z bar plus z bar over z, and this object is the usual z bar in terms of conformal cross ratios, where 2, okay, and in terms of my 1, 3, 0, this is theta, okay, and yes, and z bar is the ratio of this and this, okay. So due to this very, very nice simplification, the result for the Bosodics integral is this. So I have a sum over L plus 1, product over I, sorry, from 1 to m, sum over L. I have Li, sorry, let me make it even simpler. I have the following. I have sum over L1, Ln, integration over du1, dun. Then here I have the measure, which is the only non-factorized part inside this integrand. Okay, only non-factorized part inside the integrand is only the measure. And this gives the idea of the simplification of the problem. So I choose a basis where everything is completely factorized in one-dimensional problems apart from the measure. And then I have z bar I u1 plus un. And similarly, I can rewrite actually z over z bar to the Li plus 1 z over z bar L1 plus 1 Ln plus 1, okay, times the eigenvalue U1 L1 UN Ln to the L plus 1, where L plus 1 is the size. Okay. Now, this is the final expression in a sense that if we have only one variable, one U1 and one L1, you don't have the measure. And so you are computing the ladder, and you are in very simple situation in which you can just take a pole from the single eigenvalue you have, which is what? U equals plus minus I L plus 1 over 2, okay? So you choose pole downstairs or upstairs, depending if ZZ bar is bigger or smaller than 1. And you get immediately the result for the integrals. Otherwise, and this is where integrability kicks in, you see this measure is very special. This looks a lot like a van der Monde determinant. This almost looks like a van der Monde, but we have a plus here. Actually, if you double the variables, so you don't use m variables but 2m, you realize it like a van der Monde of a Pfaffian matrix of 2m variables. But then there is some careful computation by Basso and colleagues, recent paper, Basso, Zhong, Kosover, Dixon, I think 21, I think. And there they show that it's actually determinant of m times n matrix. And the elements of the determinant are the ladders. So this concludes the result. We have this integrability computation. And I say integrability because it's based on the separation of variable equation I wrote. I factorized in a system with n degrees of freedom in n systems of 1 degrees of freedom times a measure which couples them. But then this measure is a determinant, which is a very nice property because it can be written as elements which elements which depends each on only one U and one L, and so are ladders, and so I can compute them. Okay, and so this is the result. So I could stop here or say one other thing, which is about the OPE of the generic fishnet on the disk. It's up to you. It's short and is a combinatorical game, but up to you.
Well, okay, so let's thank him for the presentation. So I would say we can start with questions about this part, and then you can proceed with the next topic. Okay.
Okay, thank you for the nice talk. You mentioned at a certain point a supergravity approach, right? In 10 dimension. How can I see this gamma deformed theory from a dual perspective?
Okay, well, this is definitely not. I'm definitely not the right person to ask to. But if you want to know anything about the dual. The string dual of gamma deformation. I know that there is something done, but not till the limit of fishnet. So there is no way they made this deformation till the limit of fishnet. There is a work by Frolov where he works out the background for gamma deformed ADS. I mean the gamma deformed dual of the theory, but okay, Alessandro knows much more.
Maybe I'll comment a bit on it. So the gamma deformation properly defined, which is with real gammas, is what is called the TST of the deformation of the or transformation of the background. So that's something that you can get by taking 2 directions on the sphere, or many directions of the sphere if you have many gammas, and doing a T-duality, a shift, and the T-duality. So there are 2 equivalent descriptions of this. One is that it has a new background, where the part on the sphere is modified. Or you can also think of it as and that's a less geometrical way, but it's sometimes useful, the same background with twisted boundary conditions for the spheres on the for the fields on the sphere. If you want to do the actual fishnet, then you need to do imaginary gammas, which is not something which is accommodated in this description naturally. And there was some work, I think, by Basso, where he tries to sort of get some dual, starting from really the fishnet Lagrangian and trying to extrapolate it to strong coupling and get some notion that is some sort of ADS, well, some modification of ADS5 where, I mean, the ADS5 part would be more or less fine, but something would go on with the compact part. But to my knowledge, that that correspondence is not entirely understood yet. So for real gammas, I think it's completely fine. It's actually one of the simplest deformations of ADS5, process 5. But for imaginary ones, it's a little bit trickier, and I think the jury is still out.
Okay, but still the ADS5 is untouched, right? You only
The ADS5 is untouched, yes, but the trick is, I mean, in principle, you would like, I mean, maybe ideally you would like to have some sort of super geometry, right? So you would like also fermions that talk to both of them. So that's the part that is a little bit tricky.
Okay, I see. Thank you.
Can I add a comment on it?
Okay, I don't know, maybe he's going to say the same thing, that there is a realization of the fish chain. Have the
Can you hear me?
But this is not obtained as a limit. That's
if you want to have dual, is a dual.
Maybe one at a time.
Yeah.
So I think Michelangelo maybe had a comment.
Ah, okay, so can you hear, you can hear me? No, but exactly, I was going in the same direction in which I guess is Alessandro is talking, no? What I wanted to say is that, there is this description by Basso and De Liang, Zong, in which is not really understood because he's working in the neighborhood of some branch point of the spectrum, because the spectrum has some kind of branch point in which some lines are connecting to each other and then some imaginary part is arising. So in the neighborhood of this point, let's say, there is a good description doing some duality between particles and holes. So they took some old description on this duality. Anyway, the point is that the most, let's say, close picture of an ADS dual is more this string bit description made by Kolya Gromov and Amit Sever. But again, it's not like a real ADS-CFT duality, it's some kind of different ADS embed model that is reproducing the spectrum of the Bicolor theory. So it's a little bit not understood how the strong coupling is working. And Alessandro was saying right, in the sense that TST, the gamma deform has this TST interpretation of strong coupling, but when you are doing the complexification of the twist, so gamma is going to I infinity, the radius of ADS is collapsing to 0, and some crazy stuff is happening. So it looks like it's not really well understood how strong coupling is working. Sorry, I wanted to this comment. I guess also Alessandro wanted to say something.
Which one? I was going to say about this chain, exactly what you like.
maybe. I think the fish chain is on the light cone of ADS, right, Michelangelo? It's not on the boundary.
Yeah. But it's something like, let's say you are taking the graph building operator, you are writing
Yeah.
a different way, and you will end up to a model that looks like an Avogadro action that you can embed in 5 dimension and then to simulate some kind of ADS dual. I guess there is a Niccolò Primi in the audience.
Yes, but now let's not make a London party now.
Yeah. If you want to have details about this stuff, he is the right guy.
Yeah. I mean, okay.
Can you also do higher points with this?
This is great question. So yes, I cannot practically, but in principle it should. I mean, I didn't do this yet, but the idea is that this technology can be applied to compute an object which, for example, a Bosodics diagram with split legs. Now, in the same way that ladders describe, for example, the correlator by Frank Coronado, or in general, ladders are very important dual conformal integrals in amplitudes. at least at the first few loops, we have only ladders. And then, okay, you have this tennis court and other integrals. But if you, for example, 5-point function, so 5-point amplitude, 6-point amplitude, and so on, of course there are other diagrams which kicks in, but ladders are already a very good portion of them. First point. Second point, maybe some limit in which only the ladders contribute. And even if not, it's already the diagrams that split ladders, of course, higher point. In any case, these are quantities to be computed. If one wants to repeat somehow the octagon story with more edges. Okay. For the decagon, for example, yeah. What basis for a decagon at 2 loops? You have split ladder and pentaladder. Right? Pentaladder is not of this type, but I don't exclude that a ladder is exactly of this type. So I take the ladder and split 2 points.
But isn't this true only for plane kinematics? Like you are in a simpler kinematical regime, so this will be true, but in some region where you have done some special choice for one of the 5 kinematics.
This is possible. But
so
no, sorry.
At 4 points you're lucky and this works for also the normal kinematics, but at 5 points I think you need to be on the plane to make this work.
This is possible.
Okay. No, but you could do it, but you could only in this. I mean, what I'm asking is that you would use the BMN representation and do all the thing that you did at 4 points at 5, get everything, but that would only work if you are like in a special kinematical regime. So you will get like a subset or not.
Why? Sorry. What are the dual conformal integrals that enters a 5-point correlator in n equals to 4? What can they be? If it's true that only dual conformal integral contribute, it's not many. At least in the first few loops, it's really not many. Okay, and these are typically so in 4-point are ladder. So take the 4.1, start splitting legs. You already have some of them probably, and I think the work about 5-point function by Vasco Gonçalves and Chaco Fleury, for example, they have at least at 2 loops. What are the integrals?
Yeah, my worry is that you get square roots and then thick stuff, and then you don't know how to do that. While if you're on the plane, you just don't have it. But anyway, this is very technical. Doesn't matter.
I agree with you that on the plane everything is simpler because you. Yes, I agree. I concretely agree because I face similar problems. But yeah, and I think these fishnets, they don't need to be on the plane to be computed. Absolutely not. I can tell you the algorithm how to compute split ladders. Then there is a term, so long story short, if you want to compute split ladders, split it in any way, and even split Bosodics diagram, you will have at a certain point to solve a twisted Baxter equation of SU2. So already you reduce a problem of Feynman integral to an SU2 chain. Then if you can solve twisted Baxter equation for SU2 easily, for any higher spin representation, but I mean higher spin, I mean finite spin, I mean nothing like infinite dimension. Then you can compute this diagram, I think. You can encounter like issues like double poles and so on, but I don't think so. This is finite stuff. This happens when you wrap. When you wrap is kind of mess. Even if I still believe that this method should lead with some clever regularization also to the solution of the direct channel, say, so to the wheel diagrams, or yeah, at least with some point split.
Okay, are there any other questions? Okay, if not, you said you had some more material to present. I don't know if it fits in 10 minutes.
Yeah, it definitely does. It's just a small game.
Okay, so yeah, you are welcome to proceed.
Okay. Okay, so equation of the Bosodics diagram should be more or less clear, but this is the full integral. I can do something much more simple on quite more complicated topologies, not topologies, a boundary condition. So as I was explaining, if I consider fishnets that lie on the disk, okay, which are completely the bricks for these higher point functions, because all the rest is eventually renormalization around the puncture of the two-point function of the operators inserted. So all I have to compute in order to know basically everything is any possible square lattice which lies on the disk. So let me cut it in any possible way. I just draw a circle and I decide some boundary condition. The boundary condition decides, and I can say that this diagram is the only Feynman integral entering the perturbative expansion of a certain correlator, right, as a correlator just of the fields I'm cutting along the contour. Okay, so for example, here I have clearly x, x, x. These are all x fields. These are all x bar field. These are all z, and these are all z bar. Probably a careful listener noticed that I switched what is the bad and the good vertex 3 times probably. I hope I'm coming back to the initial choice, but anyways, important is that it's only one of them. Okay, so what is the difference respect to the Bosodics of this diagram here? Well, it's almost a Bosodics actually. I didn't do a great job. Okay. 3, 4, right? So here, this is the difference, right? Okay. Basically, I take Bosodics integral, which is x4, z bar 4, x bar 4, z4, and then what I do is adding, so it's changing here, right? Because here I have x bar, z, but then I have again, okay, so I have x bar, z, and then I have x bar, and then I have z, and then I have x, and then I have z square, okay? X, okay? 1, 4, 4, and then 5, yes. This is the object. Now, this is planar, of course, if it's planar if I put all these fields. For example, I can start pinching fields like in Bosodics, and I put all these fields into the same point, all these fields into the same point, and so on. Okay? These fields to the same point. This is here, this is here, this is here, this is here. Now I can ask myself what happens, and let's compare to the Bosodics. Oh, okay, so now, what is the OPE? So this is an 8-point function, actually. So, in principle, a scary object, but its OP is very simple to compute. Is the leading log of the OP. What happens in the case of the Bosodics integral? So you can conjecture that this object has 12 vertices. Okay? So the leading log would be something like log u to the 12, where u goes to 0. So u is basically the cross ratio 1, 2, 3, 4 over other two distances. Okay. Over 12 factorial of what? Of the number of a counting problem. Okay? Because here I have this bundle. Oh, sorry. Yeah, here I have this bundle. Okay? And here I have now, because I put points together, this bundle. I'm just putting 2 into 1. and 3 and 4 into 3. Okay. So the idea is that I have to count. So what is the interaction here? The only possible interaction is a field of this type crossing in only one way possible, in only one direction, so in a chiral way, a field of the other type. Okay? Or vice versa, like a field of this type crossing one of the other. Mm-hmm. So here I have three fields that cross. And that should cross 4 of the other fields and come to this final configuration. Now this can be represented as a random walk of hard magnons. Why? So how to count in how many ways this can happen without fields of the same type crossing themselves, because I don't have this vertex. Okay? So it's clear that let me describe this state. So here are 4 guys, like here, and I can write like 4 white empty circle, and then here I have 3 bullets. So what can happen? First step. The only thing that can happen in the first step, if time goes in this direction, so I go from initial to final state, is that black bullet can do 1 step left, right? This cannot, because 1 step left means crossing, means exchanging with this. So it would be crossing the vertical line. So of course, this cannot go left, because it would cross with a field of the same type, which is not allowed. And of course, also, they cannot come back after they do one, because coming back would be crossing a vertical line with the wrong vertex. So at each value of time, these 3 hard magnons can hop to the left, and this number can be conjectured, and it's not too hard to show why this makes sense, but also pictorially. Okay, what is the correction? Okay, it's action of this Hamiltonian, it's chiral Hamiltonian. So I have a chiral hopping, because only to the left, of hard magnons. How to count this? The ways in which this can happen from this state to this final state, where I have the 3 hard magnons on the left and the 4 holes to the right. Standardian Tableau. Okay. So I have a grid of 12 vertices. I write a Young diagram of 12 boxes, exactly putting 1 box centered in each vertex. And then I say the first line contains the instant of time where the first guy hops. Okay, so this is A, this is B, and this is C. I put A, B, and C. Okay, so let me make a counting. So the first thing that can happen is that first guy hops left. So at instant of time 1, for sure I'm here. And now you will see that the rule of Standardian Tableau, that means increasing in line and columns, strictly is building by itself in this model. Okay, so the second thing that can happen, okay, now my state is this. So I have 2 options. Either A goes 1 step more to the left, or this guy goes to the left. Okay, so I can have 2 here, or 2 here, for example. So if I make this choice, I have now B, and this is my new configuration. And then at this point, I have unlocked C, in a sense, right? So I could put 3 here, but I could also put 3 here or 3 here, okay? So finally, I have to count all the possible ways, so all the possible fillings of the Young tableau, of the Young diagram in the standard way, okay? And this is a solved problem, of course, with the hook length formula. So I can immediately say what is the leading log OP of a Bosodics integral. And if you compute it, it's true, by the way. And why this makes sense? It's because, I mean, the maximal log comes from, okay. Here I have gamma, right? Maximal log, I want, so here it would be G coupling, G squared to the 12. So I should derive 12 times in order to have log to the 12. And of course, so log to the 12, and then it's exponential. So I have 12 factorial downstairs. And then here I would have kind of gamma 1 to the, this would be kind of, yes, gamma 1 to the 12. So in a sense, you can write this like dilatation operator between the initial and final state, which are this and that, so in terms of fields, but to the power 12. So it means applying 12 times the hopping Hamiltonian, roughly speaking. So this is basically the time evolution of the system, applied 12 times, but it can do different paths. And you get this in this way. And the nice thing is that, okay, this you can verify with the computation of Bosodics. But then you can generalize to any shape. And for example, if you take this, straightforwardly, you know that this was a rectangular Young tableau. In this case, it would be the very same logic, but the Young tableau is not rectangular anymore. Actually, I made something a bit more too complicated, probably because here it is even concavities. So it's not even a Young diagram. But if I would consider, I can work it out, but it's better to give this last example in more simple situation. For example, you start from Bosodics like this, and then I say, well, I want, let's say like this. Yes. You say, well, I want a bit more. Okay. I want to deform this in this way, so higher point function. I have much more points. I take the OP, so I take all these points to be the same and all these points to be the same. I draw 1, 2, 3, 4. Yes. Sorry, I'm not seeing this, but the moral of the story is you write one box for each vertex. Okay? So the OP will be now the standard skew Young tableau. Because here, if I write a box centering each vertex, you see that now I have 1, 2, 1, 2, and 3, and then I have, oops, 1 and 2, 1 and 2, and 1 and 2. But the logic of the counting with the hopping repeats. So I have to count the number of standard Young diagrams, skew, which are filled according to the standard law. And I could generalize even with concavities, filling in a standard way objects which I cannot even call Young diagrams because they don't have any skew shape or something, which they are just diagram of boxes. So this way you conjecture the OP of any possible, this fishnet. And this was the game, the final game. Yes, thanks.
Okay, nice combinatorial trick. Any other questions? Okay. Michelangelo, do you have other remarks?
No, I was clapping my hand, but yes, sure. I can maybe say ask something about like how is possible, if it's possible to generalize this stuff in the dimension, because looks like you have freedom to consider Bosodics in the dimension respect to 4, and if you can say something about the dimension.
Yeah, what you, in general.
Yeah, in general, in the sense like if you have some hints or if the same procedure of this Bosodics computation can be done in general in the dimension, or is something that is very related with the 4 dimensions?
Well, there is a paper. We have done a paper with this, right? But unfortunately, what is the concrete answer is that in 2 dimensions, you can define a fishnet theory if you give up also locality in any dimension in principle, or in any even dimension in a cleaner way, say. But also in any dimension, you can define it and you can write down these integrals. And in principle, you could also not care about the existence of an underlying theory. They are integrals. The only thing you impose is that the vertex is dimensionless. So the sum of the powers of the propagator is equal to the dimension of the space-time or the space. Now, these objects, these Bosodics, you can compute in 2 dimensions. They can be written as a determinant. And it's not surprising that things are simple in 2 dimension, you may argue. But in 4 dimension, they can, and this is even simpler. In 4 dimension, they can, as I discussed, but starting from 6, from 5, or even 3, actually, odd dimension, never. But even 6, 8, so even higher dimension, it is, we don't know how to compute this integral till the very end and write them really as a determinant of functions that we can compute. We have a representation, which is written in the paper with Guenel Ferrando and Sergei Derkachev. And this representation is already very clean in a sense, but there are some extra integration parameters. Say, and this is due, if you want, to the fact that Gegenbauer polynomials in 4 dimension and in 2 dimension are simple. In 2 dimension they are even trivial, but in 4 dimension they are simple objects to handle. And Gegenbauer polynomials, as I was explaining, or symmetric traces tensor, spherical harmonics, are very important objects in my construction, in our construction. But in 3, 5, 6, and so on are much more complicated objects in the sense that they don't have those nice simple properties that we have in 4 dimension. So at some steps in our proof cannot be repeated. Okay.
Thank you. Okay, so if I run with questions, let's thank Enrico again.
Thank you.